We claim that complex manifolds have natural orientation. Complex manifolds are all orientable. And to show that, it suffices to show that holomorphic maps preserves orientation, because then the coordinate maps preserves orientation, so we can transfer the orientation from Cn to our complex manifold. So let's see why holomorphic maps preserve orientation. Recall previously we said that a smooth maps between complex manifolds always induces a map on the real tangent spaces, right? And that induces a map on the complex tangent spaces by just tensoring with C. However, it does not always induce a map on the holomorphic tangent spaces. The image of this holomorphic tangent space might not lie inside this homomorphic tangent space. And we define holomorphic maps to be exactly those for which we have an induced map on holomorphic tangent spaces, i.e. the image of this holomorphic tangent space under this map, linear map, lies inside this holomorphic tangent space. So let's suppose that F is a holomorphic map between these two complex manifolds. To show that F preserves orientation, we need to show that the real Jacobian of F has positive determinant. Remember, an orientation on each tangent space here is just an equivalence class of bases. And two bases are equivalent if the change of basis matrix between them has positive determinant. Now let's find that Jacobian in terms of coordinates. So if we let zj be the complex coordinate on x and the corresponding real coordinates are xj and yj, then we have the following coordinates on the real tangent space and the following coordinates on the complex tangent space as before. Similarly, if we let wj be a complex coordinate for y and uj and vj be the real coordinates for y, then we have the following basis for the real tangent space and the complex tangent space. We claim that with respect to these real bases, the Jacobian matrix has the following form. And let's see why that is. So the columns of this matrix should be correspond to the image of these basis element, right? So it's the coordinate of this image of this basis element in terms of this basis. So let's find the coordinate. Let's expand this in terms of this basis, partial u alpha and partial v alpha. So for example, how do we find this coordinate? Remember, the usual way is that we will pair both the left and the right hand side with a dual element of this, which is u alpha. All the other terms when we pair with u alpha will vanish, except for this will give 1. So we'll just get this coordinate here. And here we just write this as partial u alpha, partial xj. Where more accurately, we should have viewed this as u alpha composed with f. So that's the way we view u alpha as a function on x, right? So this should be the pullback of u alpha, but we don't write the f there just for conciseness. So here is actually pullback of u alpha. So that's this matrix for this linear transformation of real vector spaces. Now let's write the matrix for the linear transformation of complex vector spaces. Now the same argument works to show that the matrix of this induced map on tangent space with respect to these spaces must be of this form. However, we can simplify this further using the hypothesis that f is a holomorphic function. Remember, that means that f must sense the holomorphic tangent space inside the holomorphic tangent space, right? So that means that these bases must be sent inside the span of these bases. So we get that these parts are 0. And if we call this smaller matrix Jf, then we see that this complex Jacobian is just a block matrix with Jf and its conjugate here. And I should have said that I assume that x and y are of the same dimension, so that these are square, and we can take determinant. So I see that the determinant of this Jacobian is just gonna be the determinant of Jf, right, times the determinant of its conjugate, which is the conjugate of its determinant, so this is just a square. So the determinant is non-negative. Well, you might say, wait, but this is the Jacobian, the complex Jacobian. How about the real Jacobian? Well, these bases are also bases of the complex tangent space, so this Jacobian written in these bases will have this, by the same argument as before, we'll have this matrix. And so that means that this determinant of this Jacobian is going to be equal to the determinant of the real Jacobian. So that means that the determinant of the real Jacobian is not negative. And thus holomorphic maps are orientation preserving. Now, since X is a complex manifold, we know that locally it's biholomorphic to an open subset of Cn under a coordinate chart, and this Zj are just going to be the pullback of the coordinate functions. Now on Cn we have a natural orientation given by this top form, and so this also is then defined to be the natural orientation on X. In terms of the complex coordinate Zj, this orientation is given by the following top form. Thus, any complex manifold has a natural orientation which is preserved under holomorphic maps.